Welcome to section 5.3. We're solving trig equations. So we're working with the identities that we've done for the last two sections, and then basically we're solving them to figure out what places on the unit circle then would get those exact values. And so I want to start with the first one, and we're going to look at a unit circle. We're just going to kind of draw this basic. And we're going to say, okay, here's my angle of pi over 4. Okay? Now the question is, what is the sine at that angle? Well, we know the sine is the square root of 2 over 2. And so the question is, where else is the sine going to be a positive square root of 2 over 2? Well, all students take calculus. Where else is a sine positive? Sine is also positive in the second quadrant, and that angle then is a 3 pi over 4 angle. We're going to do the same thing for cosine and tangent. So cosine of pi over 4 is the square root of 2 over 2. Where else is cosine positive? Cosine is positive in the fourth quadrant, and so this is the angle of 7 pi over 4. You could also write it as negative pi over 4, and the reason I write it like this is because of our inverse trig functions. Because I know that the inverse sine is defined between negative pi over 2 and pi over 2. And they're going to give you an angle as a negative angle, so that's why we say the negative pi over 4. Although most of the time, if you just look at the circle, you say it's at 7 pi over 4. But I want you to know why, again, I throw that negative in there. The third question says, what is the tangent at pi over 4? The tangent is 1. I know I didn't ask that, but where else would you get a positive tangent value? And the positive tangent ends in the third quadrant, and so that occurs at 5 pi over 4 if I'm looking for another angle there. Okay, we're going to do the same thing with a pi over 3 and the same thing with pi over 6, just to kind of get us in the thought. Pi over 3 is the same thing as 60 degrees. So if I look at this pi over 3 angle, what is the sine of pi over 3? Well, let's go our pattern. 3, 2, 1. So this is 1/2 square root of 3 over 2 is my coordinate point. So the sine is the y value, so the square root of 3 over 2. Where else is sine positive? Again, we talked about that above. Sine is positive in the second quadrant. So 1 pi over 3, this ends at 2 pi over 3. Is the other angle where the sine is positive square root of 3 over 2. Cosine of pi over 3 is 1/2, and cosine is positive in the fourth quadrant. And so the other angle here, normally we think of it as 5 pi over 3. Again, I'm going to look at this and say, okay, you could also write it as negative pi over 3. But most of the time, 5 pi over 3 will be fine. The biggest thing, let's talk about tangent. Tangent is sine over cosine. So the square root of 3 over 2 divided by 1/2 is the same thing as the square root of 3 over 2 times 2 over 1. And you get the square root of 3 over 1, which is just the square root of 3. Okay, where else then would you get that positive angle? That positive angle then would occur in the third quadrant. And so this is 4 pi over 3. Sorry, as I'm thinking about that a second. There's the other angle where tangent would be positive. Okay, so let's do one more thing. Let's try the pi over 6, and then we'll actually get into today's lesson. As you look again, a unit circle, pi over 6 is the same thing as 30 degrees, so we're looking at this angle. The sine is 1/2. The cosine is square root of 3 over 2. Where else is sine positive? Sine is positive in the second quadrant. Okay, so this is at 5 pi over 6. Cosine is positive in the fourth quadrant, which is 11 pi over 6. or you could say negative pi over 6 if you needed. The tangent is sine divided by cosine. So 1/2 times 2 over the square root of 3. 1 over the square root of 3 then has to be rationalized. So you get the square root of 3 over 3. Okay, and so as we go through, this is the idea. Once you find the tangent of something equals whatever, you're trying to find the exact value or where it occurs on the unit circle. So as we go through, the goal of solving, normally when we solve for x. Well, if we're solving a trig equation, we're going to isolate, is the word we use, isolate the trig function, or basically get the trig function by itself like we would have normally gotten x by itself. So if you take a look at number 1, let's start by we want the sine of x to be by itself. So I'm going to first move 1, and so I have 2 times the sine of x equals 1, and if I divide by 2, the sine of x then equals 1/2. Now the question here is, when on my unit circle does the sine equal 1/2? We'll take a look directly above. The sine is 1/2 at pi over 6 or 5 pi over 6. So we need to look at the fact that the sine of x is 1/2, and we just showed in 2 different places, at pi over 6 and at 5 pi over 6. And so what we're saying is x equals pi over 6, and I'm going to write these separate for a reason, 5 pi over 6. So I look at the 2 places on the unit circle where I can get that angle. Now the biggest thing is we want to talk about all of the possible solutions, not just the solutions in one revolution of the circle or just from 0 to 2 pi. We want to look at all solutions. And if I'm looking at all solutions, that means I'm looking for basically all coterminal versions of that angle. So I have this. Sine has a period of 2 pi, which means if I start at pi over 6 and I go 2 pi, that's a coterminal angle of 13 pi over 6. And then if I go another pi, or 2 pi, I can get another angle. And if I go another 2 pi, I get another angle. These are all coterminal angles. Because the period is 2 pi, I'm going to also say plus 2 pi n, because every multiple of 2 pi gets me another multiple of that angle, which is still a solution. Same thing for this 5 pi over 6. I could go all the way around. That's another angle, and another angle, and another angle. And there are infinitely many of those coterminal angles for 5 pi over 6. So I say 5 pi over 6 plus 2 pi n as well, because again, we are accounting for all solutions. Now, if they were just to ask between 0 and 2 pi, I would say pi over 6 and 5 pi over 6. But because they're asking for all of them, then I need to include the 2 pi n. Okay, let me show you the same thing with a tangent. Again, I want this trig function to be by itself, so I'm going to add 1. 3 times the tangent squared of x equals 1, and I divide by 3, so the tangent squared of x equals 1/3. And I don't want tangent squared, so I'm going to square root this. Now, I get the tangent of x equals, now every time you square root, you should have a plus or a minus. And if I break this apart, the square root of 1 is 1 over the square root of 3. And I don't necessarily like this, so we're going to rationalize. So we're looking for the square root of 3 over 3. And so we're going to go to our unit circle and figure out when do I get both a positive tangent and a negative tangent. Now again, take a look. We said the tangent at pi over 6 gave us the square root of 3 over 3. Now, not always are you going to have these tangent values. So here's what I do when I'm trying to figure out a tangent value. I look back at this fraction, 1 over the square root of 3. And I say what had to be on top and what had to be on bottom for that to work out. Well, because there's a 1 on top, the 1/2 had to come first, and then the square root of 3 over 2 so that the 2's would cancel. So that means the sine occurs at 1/2 and the cosine occurs at the square root of 3 over 2. And so that's kind of the way that I look at it is, okay, if a 1's on top, 1/2 had to be on top. If it were just the square root of 3, I could put this over 1. That says I divided the square root of 3 over 2 by 1/2. And so that's kind of the thought process going through. Now again, sine is 1/2, cosine is square root of 3 over 2, occurs at 30 degrees or pi over 6. And we really would like your angles in radians today. So I'm looking basically at every multiple of pi over 6 because I have the plus and minus. And so as I go through, I'm going to kind of look at kind of the big ones. I have, first of all, pi over 6. And the period for tangent, this period is pi. So when I go there, I'm going to say pi over 6 plus pi n, every multiple of pi, because that's the period. But now take a look, where did that give me? That gave me this pi over 6 here, and if I go a full pi, I'm down in the third quadrant over here. Well, now those gave me the positive tangents. What gives me the negative tangents? Well, the negative tangent, let's start up here. We want to go to the first angle we get to. This is 5 pi over 6. So there's my other angle, plus, if I go another pi, I get back to here at 11 pi over 6, and this one accounts for the negatives. So these are the two positive angles, these are the two negative angles. And that gives me all 4. The biggest thing to remember though is once you square root, you have this plus and minus that you have to account for. Tangent's period of pi already includes then the other two angles that we don't have listed. But you want to include the period then as you're going through. All right, let's move to the next page. For some trig equations, you will need to write them though so that they have a single trig ratio. Okay, and this is kind of what we did in section 5.1. If you look, I have both a sine squared and a cosine, which is bad. And we said in section 1, only replace the squared term. Well, I know that sine squared is 1 minus cosine squared, according to my Pythagorean identity. So I'm going to replace that, and I'm going to put the 2 in, and now I'm going to simplify this a little bit. So I have 2 minus 2 cosine squared plus 3 cosine minus 3. I'm going to combine like terms, but the biggest thing is I don't necessarily want a negative in front. And so what I'm going to do is I'm also going to multiply everything by -1 so that I get that negative out. So the 2 and the -3, this basically makes -1. So if I multiply everything by a -1, I get 2 times the cosine of squared of x minus 3 times the cosine of x, and it was a -1 when I added these two together, so +1. Now, because I now have this in terms of a squared and a single and a number, I can think of it in terms of factoring. This is really saying x squared, or 2x squared, minus 3x plus 1, and you could factor this. So I'm looking to factor this. So 2 cosine squared is 2 cosine times 1 cosine. To get 1, I only have 1 times 1, but these have to be negative to add to a -3. So because these two are the same, it won't matter the order, I'm just putting it in. So I have 2 times the cosine of x minus 1, and the cosine of x minus 1 equals 0. And I'm going to work on factoring these basically, or setting these both equal to 0. So 2 times the cosine of x minus 1 equals 0. And the cosine of x minus 1 equals 0. Now I'm going to start with this right one because it's a little quicker and easier. if I add 1 first, we're asking where does the cosine equal 1? All right, think about the unit circle. Cosine is the x value. So where does the cosine equal 1? It occurs at both 0 and at 2 pi. Well, I don't want to say 0 plus the period 2 pi n. I mean, you could say 0 plus 2 pi n. But really what I'm going to say is just 2 pi n because I don't really want to add a 0. Okay? And the reason I added 2 pi n, again, is the period of cosine is 2 pi. So I look at the second one, and I add 1, and I basically divide by 2. The cosine of x is 1/2. So where is the cosine 1/2? 1/2 is the x value. So it happens at pi over 3 or 60 degrees, and then cosine is also positive in the fourth quadrant, so 5 pi over 3. Now again, the period of cosine is 2 pi, so my two answers are going to say pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. And so actually what happens here, normally we think we have two answers because it's a squared. With trig values though, you have 3, and looking at this, you've got 1 here, pi over 3, 5 pi over 3, and 2 pi n. Sorry about that. The fourth one, I look at cotangent times cosine squared equals 2 times cotangent. Okay, I would like to get these both on one side because I want to set it equal to 0 like we had in number 3 to be able to do something. So I'm going to move 2 times the cotangent over. So the cotangent times the cosine squared minus 2 times the cotangent equals 0. All right, as I look at this, what I notice is I have a cotangent in common. So I'm going to pull the cotangent out, and I'm left with cosine squared minus 2 equals 0. And I'm going to set each of these factors then equal to 0. So I'm going to say, okay, when does the cotangent equal 0? And when does cosine squared minus 2 equal 0? Well, cotangent is the same thing as cosine over sine. So if I want this to equal 0, then the cosine has to equal 0, because the sine can't, or I have an undefined fraction. So where is the cosine equal to 0? Cosine is x, so the cosine occurs at pi over 2 and 3 pi over 2. Now let's talk about period. The cotangent has a period of pi. And so if I take pi over 2 and add pi to it, I get to 3 pi over 2, so I don't need a separate anything. I can just say then pi over 2 plus pi n, and that accounts for this 0 as well. The second one is cosine, so I'm going to set this equal to 2. Cosine squared equals 2. And when I square root, I get that the cosine is plus or minus the square root of 2. Now, let's talk about this. Cosine, they're asking you basically what angle gives me a value that's the square root of 2. If you think about it, cosine values, though, occur between -1 and 1. The cosine of 2 is bigger than 1. And so this is not possible because the square root of 2 is bigger than what the domain of a cosine is. So, cross this thing out. We are done. We only have one solution in this case, pi over 2 plus pi n. All right, let's take a look at 5. We get a little harder, and I don't want to say it's too much harder. It's just the end result that's going to be different. Our process is still the same, though. We would like this cosine to be by itself, so we're going to add 1. 2 times the cosine of 3x equals 1. When I divide by 2, the cosine of 3x equals 1/2. Now here's what's going to happen. We normally then say, okay, where does a normal cosine equal 1/2? And we're going to do the same thing. I'm going to now, instead of saying x equals, I'm going to say 3x equals. So look at your unit circle. Pretend that this is just an x for a second, not the 3x. Where is the x value going to give you 1/2? Well, that occurs in 60 degrees. So at pi over 3, and cosine is also positive at 5 pi over 3. Now, the only difference is instead of setting it equal to x, we set it now equal to 3x. Our period is 2 pi, so we say plus 2 pi n. And all I'm going to do now is get rid of the 3. So I'm going to multiply this side by 1/3, and I'm going to multiply my entire quantity over here by 1/3. So I get, in my first one, well, pi over 3 times 1/3 is pi over 9, and plus 2 pi n over 3. That's my first one. My second one, do the same thing. 5 pi over 9 plus 2 pi n over 3. These are my solutions, and they're different. Again, they are horizontally shrunk inward because of the 3 that's there. So the only difference, if you see a number tied with the x, you still find on the unit circle where you get that exact value. Then you just basically set it equal to the 3x and multiply it through. One more that's slightly more difficult. Again, I want to take a look at this one because the two trig values are different. And so we need to replace them like we did above. So I know that secant squared is the same thing as 1 plus tangent squared. And so I'm going to start there. Okay, I'm also going to set this equal to 0. So I have, and I'm going to write this in order, tangent squared minus 2 times the tangent, negative 4 and 1 equals negative 3 will equal 0. All right, and I'm going to factor this just like I normally would. Tangent squared is a tangent times a tangent. Negative 3 is negative 3 and positive 1, since you have to add to a negative 2. So I have the tangent of x minus 3 times the tangent of x minus 1 equals 0. All right, here we go. We add 3. So the tangent of x equals 3. Now the only problem is I don't know. 3 is not an exact value on our unit circle. So this is where our inverse functions kind of come into play, because if I'm trying to find this angle x, what I'm going to do then to find x is take the inverse tangent of my value in order to find the angle. And truthfully, I don't want to know the angle, I don't want the decimal. All I want to know is, okay, can I do this? And so in order to find the angle, I know I can because the domain of a tangent is from negative infinity to infinity. So that's definitely a value. So I'm okay there. Plus, I can't forget my period of tangent is pi n. And I know this is kind of a weird way to leave it, but since it's not on the unit circle, I'd actually like it left that way. The second thing, as we set this, the tangent of x equals 1, and I just moved the 1 already, where does tangent equal a positive 1? Well, the tangent equals a positive 1 at pi over 4 and, let me change that again, 5 pi over 4, because it occurs in the first quadrant and the third quadrant. Now the period of tangent is pi. So if I save pi over 4 plus pi n, when I add a pi, I get here to the 5 pi over 4, so I don't need to separate that because my one equation for the answer would give me that value. And this is the trickier one here where you say the inverse tangent of 3, just because you're going to get a decimal when you put it in your calculator for a radian. The decimal is not going to end, and so it's just not necessarily worth writing it. You can just leave it as the inverse tangent of 3. But again, our goal is to find the angle. All right, last one that we're looking at is extraneous solutions. The only time you need to check for extraneous solutions is when you square both sides of an equation, okay? Now, the reason we talk about squaring both sides of the equation is if you look at the example, cosine x plus 1 equals sine. The problem with this is you cannot replace one of the trig values for the other because they're not squared. And the only time you can replace them with a Pythagorean identity is if you have cosine squared or sine squared. So because I don't have that option, the only thing I can do is to square both sides. Okay, now please be careful when you square both sides, because when you square this, you have to FOIL. So you get cosine squared plus 2 times the cosine plus 1 equals the sine squared of x. Now here you notice I have cosines on this, I have multiple cosines. So I'm going to replace this sine with 1 minus cosine squared. And when I do that, I now need to move my values over. So I'm going to subtract 1, and I'm going to add a cosine squared. So I have 2 times cosine squared plus 2 times cosine, and 1 and negative 1 cancels, so I get to equal 0. Now as I look at this, okay, I only have 2 terms. What I can pull out is a 2 and a cosine. And if I pull that out of the first one, I'm left with cosine plus 1. And like I've done before, I'm going to actually just set each equal to 0. So 2 times the cosine equals 0. When I divide by 2, they're still saying the cosine equals 0. Well, where does the x value equal 0? It equals 0 at, let me move this up, it equals 0 at pi over 2 and 3 pi over 2, because those are the x values. And for this question, let's go from 0 to 2 pi. And I'm going to put a parentheses here because 0 and 2 pi are the same thing, so I only want it recorded as one of them. And I don't care which way you write it, but I only want one of those. So in this case, here's my answer for the cosine. If I look at this one, the cosine of x equals negative 1. So where is the x value negative 1? This occurs at pi. So I have this angle then as my answer there. Now, because we squared both sides, we do need to check and make sure, do all 3 of these work? And so let's look at the check, because I want to show you what that looks like. I'm going to start with pi over 2. So our question is, the cosine of pi over 2 plus 1, does it equal the sine at pi over 2? Well, the cosine of pi over 2 is 0, plus 1, and the sine of pi over 2 is the y value equals 1. The answer is yes. So my solutions, I'm just going to start a list of them. My solutions, I have 1 at pi over 2. All right, let's check the next one at 3 pi over 2. The cosine of 3 pi over 2 plus 1, does it equal the sine at 3 pi over 2? All right, well, the cosine at 3 pi over 2 is 0. 0 plus 1, but the sine at 3 pi over 2 is negative 1. And the answer in this case is no. So that's our extraneous solution so far, because 3 pi over 2 doesn't check back in. Let's go one more. Cosine of pi plus 1 equals the sine of pi. Well, the cosine at pi is negative 1, plus 1 is 0. Does that equal the sine of pi, which is 0? And the answer is yes. So my other solution then is pi. And so the point of this, again, if you square it, if you don't have a squared somewhere to start, and you can't replace values, then you have to look at squaring both sides. If you square both sides, then you need to check the answers that you got back in the original to make sure they work. So that's section 5.3, and this is really why we spent all that time doing the trig identities and factoring and replacing things, is to be able to look at this now and say, okay, how can I use it to solve? So take a second, start the 5.3 homework. That will be the biggest help to you, but that's all for section 5.